Imagine taking a perfectly empty glass light bulb, sealing it in a vacuum, and removing every particle of matter. According to the mathematics of quantum theory, the empty space inside that bulb still contains approximately 10 to the 93rd power grams of energy per cubic centimeter. A single light bulb-sized volume of nothing holds more energy than the entire observable universe. This density is a direct result of how quantum mechanics describes the vacuum. Because of the Heisenberg uncertainty principle, a field can never be perfectly still. Physicists model every point in space as a tiny mathematical spring that must maintain a small amount of residual motion, even in its lowest state. These vibrations generate zero-point energy, a baseline of activity that exists even in total darkness. Albert Einstein's general relativity tells us that energy has gravity. If the vacuum actually possessed this near-infinite energy density, the gravitational weight of empty space would have crushed the universe into a singularity a fraction of a second after the Big Bang. Stars, planets, and galaxies would have been physically impossible. Since the universe clearly exists, physicists use a process called renormalization to make their equations functional. They argue that because we only ever measure changes in energy, the absolute value of the vacuum doesn't matter. This allows them to manually subtract the infinity from their equations, treating the vacuum energy as a constant and focusing only on the particles moving through it. But when astronomers measured the actual expansion of the universe, they found that the real energy of the vacuum is tiny, but non-zero. This leaves a gap between quantum prediction and cosmic reality of 10 to the 120th power. This vacuum catastrophe represents the largest discrepancy between theory and observation in the history of science. One proposed solution is that mass only comes into being during a wave function collapse. However, in our current best models, gravity does not wait for an observer to act. Space-time curves in response to the mathematical expectation value of a vacuum's energy, meaning the energy of the field is an always-on property that warps the universe even when it is unmeasured. Furthermore, the universe does not require a conscious mind to function. Through quantum decoherence, any physical interaction acts as a measurement. When a cosmic ray hits a dust particle or a photon bounces off an atom, information leaks into the environment. The cosmos is a dense network of interactions that is constantly observing itself. Sir Roger Penrose offers a different perspective, suggesting that gravity itself is the trigger for wave function collapse. In this speculative model, a superposition of mass separates space-time into incompatible geometries. Once that separation reaches a critical threshold of instability, the universe forces a collapse. In this view, mass triggers the reduction of the wave. If these spontaneous collapses happen without a measurement device to exchange energy with, they would create a tiny, continuous amount of kinetic energy, a phenomenon called anomalous heating. Experimental physicists are currently cooling metal blocks to near absolute zero in underground labs, searching for this exact unexplained heating effect to prove if objective collapse is a physical reality. This leads to a radical cosmological hypothesis. We know that during the inflationary epoch of the Big Bang, a massive, unstable vacuum energy decayed and dumped its potential into the creation of particles. It is mathematically possible that all the matter we see today is literally leaked energy from that primordial, energy-dense quantum vacuum. Whether the vacuum is slowly bleeding energy into matter or perfectly conserving its baseline, our classical assumptions are inadequate. The 10 to the 120th power energy gap proves that we are missing a fundamental piece of how gravity and quantum fields interface. This mismatch extends to how we view the container of the universe itself. The idea of an expanding universe sounds incoherent because we assume for something to expand, it needs a larger, pre-existing space to expand into. This diagram shows the metric expansion of the universe. In general relativity, space is a mathematical grid. The galaxies aren't flying apart through a void. Rather, the space between them is being generated internally. The scale factor, the distance between coordinate lines, increases over time. Because the math describes internal stretching, the universe can have a closed global shape, like a three-dimensional torus. In this donut-shaped model, space is finite but has no edge. A ship traveling in a straight line would eventually loop back to its starting point, stretching internally without ever needing an outside to move into. String theory takes this enfolded geometry even further, speculating that the entire universe has up to 11 dimensions. While we experience 3 macroscopic spatial dimensions, the others are compactified into unimaginably small, complex shapes called Calabi-Yau manifolds. These tiny dimensions are tucked away at every single point in space, hidden beneath the surface of our 3D reality. The expanding into what paradox dissolves when we look past our three-dimensional intuition. The universe isn't a bubble in a room. It is a mathematical structure defined by its internal stretching and higher dimensional folding. Projective geometry provides another way to resolve this, by mathematically baking infinity into the structure of space. By defining a point-at-infinity boundary, this branch of math creates a self-contained universe that doesn't require more room to expand, because the boundary is part of its internal geometry. In the late 19th century, Rudolf Steiner used these principles to propose a model of counterspace. He argued that if matter and gravity radiate outward from a point, there must be a mirrored reality where forces pull inward from the infinite periphery. He associated this ethereal space with a constant, omnipresent pressure acting from the boundaries of the universe. This concept of an inward pull mirrors the modern mathematics of chaos theory. In a chaotic system, movement is governed by a strange attractor, an invisible fractal shape in phase space. The system is drawn towards this attractor, not because something is physically pushing it, but because the overarching mathematical geometry of the space compels it to move that way. Steiner's counterspace and the strange attractor both describe a universe driven by a global geometric pull rather than local forces. If we view the quantum vacuum as a kind of strange attractor, the vacuum catastrophe looks different. Perhaps the immense zero-point energy is a cosmic attractor constantly pulling reality towards its ground state. The universe would be caught in the restless orbit of this attractor, endlessly fluctuating because the vacuum itself is filled with chaotic energy. Viewing the vacuum as a teleological engine pulling from infinity suggests the universe is not just a collection of objects bumping into each other, but a unified system guided by invisible, overarching structures. The 120 order of magnitude energy gap remains a profound, unresolved mystery. It serves as definitive proof that our current understanding of how gravity and quantum fields interact is fundamentally incomplete. Physicists are now searching for a theory of quantum gravity, a framework that can reconcile the smooth curvature of general relativity with the violent fluctuations of the vacuum. This requires us to move past our classical intuition and embrace radical new geometries. Our universe operates as a dense, unified engine defined by invisible geometric pulls, endless energy exchange, and structural mysteries we are only beginning to witness.